This animation shows the NeoMovies app interface. Notice the seamless scrolling through the popular and top-rated movie lists. On the surface, the user experience appears effortless. High-resolution movie posters load instantly from the network, and system themes like dark mode toggle without a single frame of lag. But that smooth presentation on the glass masks a highly complex asynchronous orchestration operating underneath. To achieve this, the application has to coordinate network requests, local database caching, and background thread management all at exactly the same time. Attempting to build this exact experience using legacy Android patterns, relying on XML layouts, manually managing the UI thread, and juggling fragmented lifecycles often results in a fragile, crash-prone application. To understand how modern Android applications achieve strict stability, we have to deconstruct the specific modern Android development, or MAD, libraries that replaced that legacy stack. The architecture of this repository relies on a specific set of tools: Jetpack Compose for the interface, Kotlin coroutines for background tasks, Room for local data storage, Retrofit for network calls, and Datastore for user preferences. Together, these libraries represent a complete structural shift. They move Android development away from imperative UI updates, where you manually command the screen to draw specific elements, and toward a reactive, unidirectional data flow model. This diagram illustrates unidirectional data flow. User events flow strictly upward to a logic center, and application state flows strictly downward to update the UI. This strict loop prevents state inconsistencies. We can trace this backward to the local database. Mastering these modern libraries requires looking past the basic syntax to see how they enforce strict architectural boundaries. Starting at the top of the architecture in the presentation layer, you will notice the explicit removal of all Android fragments and XML layout files. Instead, the repository utilizes a single activity architecture. It relies entirely on Jetpack Compose, which is Android's modern toolkit for building native UI using entirely Kotlin code. Compose is declarative. The UI components do not fetch or own any data themselves. They merely observe state objects and automatically recompose or redraw themselves whenever that underlying state mutates. To handle the visual assets, the app integrates the accompanist Glide library. Glide is an image loading framework, and this integration bridges the gap by loading the high-resolution TMDB network images directly into these stateless Compose components. Migrating to this pure Compose architecture eliminates the notoriously complex fragment lifecycle. By doing so, it removes a major source of memory leaks and crash reports. By making the UI completely passive and strictly declarative, the architecture successfully shifts the entire burden of logical complexity down into the V model. Moving down to the domain tier, we find the V model. The V model is an architectural component designed to store and manage UI-related data, acting as the orchestrator of the app's reactive state. The engine driving this orchestration relies on Kotlin coroutines. Coroutines are a concurrency design pattern that allow the app to execute complex, long-running background tasks without blocking the main UI thread. This diagram shows layers connecting using Kotlin Flow, an asynchronous stream emitting sequential values for real-time reactivity. The repository uses this mechanism for internet connection monitoring. When a network drop occurs, the monitor instantly updates the vModel state, eliminating the need for fragile callback functions. Together, Flow and coroutines act as the application's nervous system. They replace convoluted callback chains with robust, lifecycle-aware data streams. That brings us to the final bottom tier, the data layer. This is exactly where the actual information is sourced when the vModel requests the initial popular movies payload. The app relies on Retrofit to communicate with the outside world. Retrofit is a type-safe REST client for Android that executes the TMDB API network requests and logs the incoming traffic. Integrated directly into that Retrofit pipeline is Moshi. Moshi is a modern JSON parsing engine designed specifically for Android and Kotlin. Moshi is necessary because it safely and efficiently converts the massive, unpredictable JSON responses from the TMDB servers into strictly typed Kotlin data classes. Enforcing the use of typed data classes right at the network boundary ensures that missing fields or malformed data are caught immediately, preventing null pointer exceptions from propagating up into the UI layer. Retrofit and Moshi act as the strict gatekeepers of the app. They ensure that only sanitized, perfectly structured data is allowed to enter the application's internal architecture. But purely network-driven applications share a critical flaw. They break the moment the user loses their internet access. To solve this, the app uses the Room database. Room is an abstraction layer over SQLite that serves as the core component of the app's offline caching strategy, and it provides local storage for saving user-liked movies. This diagram illustrates the single source of truth pattern. Retrofit fetches network data, saving it exclusively to Room. Room then emits the flow upward to the view model. Behind the scenes, Work Manager silently refreshes this data daily, highly optimizing user battery life and minimizing bandwidth. Beyond caching movie data, the app also has a secondary persistence requirement, saving localized user preferences like the state of the dark mode toggle. For this, the repository explicitly abandons legacy shared preferences in favor of Preferences Data Store. Data Store provides asynchronous, type-safe preference saving using coroutines, eliminating the blocking operations of the older system. By layering Room, Work Manager, and Data Store, the application guarantees an instantly responsive UI. It entirely abstracts network latency away from the user. We can now zoom out and view this entire architectural stack operating simultaneously. Let's trace a specific user action, opening the application to view the movie list. This diagram traces the sequence. The UI signals the vModel, which launches a coroutine to request data from the repository layer. The repository first checks the local Room database. Finding the cache stale, it commands Retrofit to fetch fresh data from the TMDB servers. Moshi parses the incoming JSON response, and the Room database immediately updates its internal tables with the new information. Because Room acts as the single source of truth, it automatically emits the new data upward via flow. The view model then transforms that raw data into a localized UI state. Finally, Jetpack Compose observes this new state flow and instantly recomposes the screen to display the updated movie posters. This perfectly choreographed, strictly predictable sequence of data events is the ultimate goal when building apps with modern Android development. This entire architecture is built on absolute decoupling. The Compose UI knows absolutely nothing about TMDB or Retrofit. It merely blindly renders whatever state flow it is handed by the view model. Conversely, the network layer knows nothing about how the data will be displayed on the screen. It only exists to fetch JSON and feed the Room database. This rigorous separation of concerns makes the application highly modular, exceptionally testable, and deeply crash-resistant. Integrating Data Store, Room, Compose, and Work Manager within a clean architecture creates a resilient, production-grade system.